In this lesson, we're going to analyze power functions. Some of the functions you have seen already, and we will review many of the concepts previously seen in this course. So a power function is any function that can be written as f of x equals a times x to the nth power, where a and n are non-zero constant real numbers. So we've looked at polynomial functions extensively. On your screen, you are seeing monomial functions, which would be your simplest form of a polynomial function. And look at the different ways that we can talk about these functions. Particularly, these two on the top are even functions based on their end behavior. This would be where your leading coefficient is positive, leading coefficient would be negative in this scenario. Here are two odd functions, leading coefficient positive versus negative. Notice all four are continuous, so your domain is negative infinity to positive infinity, but your range will vary in each of the scenarios based on whether it's even or odd. In the 4 on your screen, your x and y intercepts are all at 0. Notice that all are continuous. As far as symmetry, this has y-axis symmetry, whereas your odd functions have symmetry about the origin. Increasing or decreasing, we talk about the x values for which it's doing that, and a reminder on how we write our end behavior. So the limit of f of x as x approaches negative infinity equals infinity, and the limit of f of x as x approaches positive infinity is also infinity, indicating that it goes up on both the left and the right. So this chart is a nice summary of the different ways that we can talk about monomial functions. So in this first example, we are going to graph and analyze the function by describing the different components that you see. So f of x is equal to 1/2 times x to the 4th. So this is a power function. We also know it as a polynomial function, a type of power function. So without even pulling out my graphing calculator, I know that the end behavior is going to go up on both sides, and it's going to look something like this. Now, I would encourage you to pause and look at it on your graphing calculator as you begin to describe it. So my domain is negative infinity to positive infinity. Here you can see the actual function graph. So the range is going from 0 to positive infinity. The x and y intercept are both at 0. You can write it as x equals 0, y equals 0. I would also accept it as an ordered pair. Okay, the end behavior on both sides are approaching positive infinity. As far as continuity, this is continuous for the entire domain values. So continuous on negative infinity to positive infinity. Where is it increasing? Well, it would be increasing from 0 to infinity for this part of the graph, and it would be decreasing from negative infinity to 0. Remember that we use parentheses when we're talking about increasing or decreasing, because a function is not increasing or decreasing at one particular point. Some other things you could be asked to describe would be any extrema. There would be an absolute minimum at 0, 0. And if you tested this algebraically, you would see that this has even symmetry. Just a quick reminder of how to do that. If you plug in negative x everywhere that there is an x and simplify, if you get just f of x, which is what we do, you can conclude that it's even. So when I raise a negative x to the 4th, I would get a positive x. So f of negative x is equal to f of x. Therefore, I do have even symmetry. That's just a reminder from some old content. Okay, it's your turn to analyze the next one. Pause and then check your answers. When you sketch this one on a graphing calculator, it ends up looking something like this. Does cross at the origin though. So you can see my answers on the screen. Notice I've crossed out increasing because this is decreasing from negative infinity to positive infinity. If you check for symmetry, it is symmetric about the origin, therefore it has odd symmetry. So let's talk about what a reciprocal function is. A reciprocal function has the form of f of x is equal to a over x. You'll also see this written as f of x equals a times x to the negative first power, because remember that a negative exponent would cause this to drop to the bottom, or cause the x to drop to the bottom. What I'm doing now is I'm making a quick xy table just to remind you of what the graph or the parent function looks like. So when we are on the negative side, I have negative 1/4, negative 3, negative 1/3, negative 2, negative 1/2, negative 1, 1. And it's undefined at 0 because I cannot divide by 0. So my graph approaches both that x and y axis. Similarly, it exists in the first quadrant, and it gets closer and closer, closer and closer, but never ever touches that x-axis nor the y-axis. So this ends up having a vertical asymptote at 0, which is what we would expect because we can't divide by 0. So there's a vertical asymptote, but notice that there's also a horizontal asymptote here at y equals 0. So we have some discontinuity with reciprocal functions. So we're going to analyze this reciprocal function here. So this would be, just so you realize, this is equivalent to negative 3 over x to the second power. So I know I'm definitely going to have a vertical asymptote because I can't divide by 0. So I am going to sketch this to analyze it. So here is a sketch from the graphing calculator of what this function looks like. So our domain, definitely we have a break, like we said, at x equals 0. So my domain will be negative infinity to 0, union 0 to infinity because of my vertical asymptote. Now the range, that goes from negative infinity and it's approaching 0. So negative infinity to 0. So x-intercept, it's never going to, it just approaches it, does not exist. My y-intercept does not exist either. My end behavior, well, because it has that horizontal asymptote, it's going to be approaching that horizontal asymptote of 0. So the limit of f of x as x approaches negative infinity is 0, and it also approaches 0 on the right. Now, as far as continuity, we definitely have discontinuity here. And what type is it? Well, this would be infinite discontinuity. And that would be at my vertical asymptote. So infinite discontinuity at x equals 0. Now, how about increasing versus decreasing? So for this first part, here it's decreasing, and then it's going to be increasing on the right. So it will be decreasing from negative infinity to 0 and increasing 0 to infinity. It's your turn for the next one. Pause, hit play when you're ready to check your answers. Here are the answers. Now we're going to analyze some functions containing rational exponents. So a rational exponent is when it's in a fraction in simplest form, so like x to the 1/3, and I just want to remind you that this is equivalent to the cube root of x, or x to the 5/4 power is equal to the 4th root of x to the 5th power. So this one is your exponent, and the denominator here is the index on the radical. I mention this because if the denominator is an even integer, then your domain is going to be restricted to non-negative values because you can't take an even root of a negative value. For instance, you can't take the square root of -4 in the real number system. So for instance, in this one, f of x equals x to the 5/2 power, I know I'm going to be taking an even root. So that's going to restrict the domain to positive values. If you take a look at this on your graphing calculator, this particular one looks like this. All right, so let's talk about this. So my domain is from 0, it could equal 0, 0 to the 5/2 is fine, to infinity. And my range then would be the same. So my x-intercept and my y-intercept hits right at 0. My end behavior. Well, the end behavior only exists on the right, so I'm going to say that the limit of f of x as x approaches positive infinity is equal to positive infinity. It does not exist on the left. All right, so how about continuity? Well, it would be continuous from 0 to infinity. Increasing versus decreasing. This does not decrease, and it's increasing on the interval for the entire domain. But again, we use parentheses when we talk about increasing versus decreasing. Some other things you might mention here would be it has an absolute minimum at 0, 0. All right, this is the final one in the video, and it's your turn. Please try it. Hit play when you're ready to check your answers. So you can see the domain goes from -infinity to 0, union 0 to infinity, because I've got a vertical asymptote, which when I got to continuity then I said infinite discontinuity at that vertical asymptote at x equals 0. Range goes from 0 to infinity. I would have a horizontal asymptote here at y equals 0. There are no x or y intercepts. The limit on both sides approaches 0. It's increasing here from -infinity to 0, and then it decreases from 0 to infinity.